Imagine this. You're standing on Mars. Not in a movie, not in a rendering on your screen. Actually there. The sky is a muted red, almost salmon-colored, with a faint hint of blue near the horizon. The sun looks smaller, colder. The ground is dust and rock and history, billions of years of it, stretched out in every direction. Now slow it down. You take a breath. Except, if you took a real breath here, it would kill you. The air is whisper-thin, less than 1% the pressure of Earth's. It's mostly carbon dioxide, so even if it were thicker, your lungs couldn't use it. There's almost no oxygen, almost no protection from radiation, almost no shielding from micrometeorites. Your spit would literally boil on your tongue if your helmet cracked. Your blood would start to fizz. And yet humanity keeps looking at this world and saying, we're going there. We are going to live here. We're going to raise children here. People will fall in love here, argue about taxes here, get old and tell stories about back on Earth, here. So here is our question for this odyssey. Is it more realistic to change an entire planet like Mars to fit us, our current, fragile, Earth-tuned bodies, or to change ourselves to fit this planet? Do we terraform Mars, or do we terraform us? I'm Rowan K. Mercer, and this is the Science Audit. Tonight we're going to run a reality check, not just on rockets and atmospheres, but on our own definition of human. Because this isn't just an engineering question. It's a question about identity. Let's set the stage clearly. When people say, terraforming Mars, they're invoking a very big idea. Terraforming literally means earth-shaping, taking a hostile world and systematically engineering it until it becomes Earth-like. Think of terrarium, an artificial little ecosystem in a glass box. Terraforming is trying to do that. Except the box is an entire planet. Self-modification, on the other hand, is what I'll call self-terraforming. Instead of reshaping the planet, we reshape the organism. That includes genetic engineering, cybernetics, radical architecture, even digital life, routes where the environment stays harsh, but we or our machines adapt to thrive in it. So here's how we'll navigate this. First, we'll walk through the physics and engineering of terraforming, what it would really mean to turn Mars into a blue-green world. Then we'll flip the lens and look at what it means to engineer ourselves, the biology, the bioethics, the cyborg futures. Then we're going to press on the paradoxes, the places where the math, the biology, and our sense of self start to pull in different directions. And finally, we'll turn that spotlight back on us and ask, what does our choice here say about what we think a human being is in the first place? So, you're on Mars. Helmet on for now. Let's start with the classic dream. Terraforming. Imagine Mars, not as it is, but as many sci-fi book covers have painted it: blue oceans pooled in the northern lowlands, clouds drifting lazily, green streaks along canyon walls, breathable air you can walk through in a t-shirt. The dream is simple to say, make Mars more like Earth. The reality, though, is that Mars is not just a cold Earth. It's an entirely different machine. Mars is smaller, about half Earth's diameter and only about a tenth of its mass. That means gravity on Mars is roughly 38% of Earth's. If you weigh 70 kilos on Earth, you'd weigh about 26 on Mars. Fun for jumping, perhaps, but it changes everything about how an atmosphere behaves, how your body grows, how your heart works. Mars also has no global magnetic field like Earth's. Our planet's core churns like a giant dynamo, generating a magnetic bubble, the magnetosphere, that deflects much of the charged particle radiation from the sun and from deep space. Mars lost that magnetic shield billions of years ago. Its atmosphere was stripped away gradually by the solar wind, like smoke being blown off a candle you never relight. Today, Mars's atmosphere is not just thin, it's also leaky. So if we want to terraform, we have a few giant tasks. Task 1, thicken the atmosphere. Right now, the pressure at the surface of Mars is similar to being at about 30 to 35 kilometers above Earth's surface. Commercial airliners cruise at around 10 to 12 kilometers. So we're talking about a stratosphere so thin even a goose couldn't migrate through it. We need to increase the pressure by at least a factor of, say, 10 to 100 just to reach something where you could, with some acclimatization, potentially survive without a full pressure suit. And that air needs to contain oxygen at a partial pressure your lungs can use. That means more gas. Where do you get a planetary atmosphere's worth of gas? On paper, there are options. You could heat Mars up enough to release CO2 trapped in its polar caps and in frozen soil, letting it sublime, go straight from ice to gas, and puff up the atmosphere. You could import volatiles, icy comets, nitrogen-rich asteroids, chunks of the outer solar system, and smash them into Mars, each impact delivering water, nitrogen, and other gases. You could build factories, literally planet-scale chemical plants, that pump greenhouse gases into the sky, like supercharged versions of the worst things we've accidentally done on Earth, but this time on purpose. But here's where scale hits. If you've ever tried to warm up a cold room with a candle, you know how feeble that feels. Terraforming Mars is like trying to heat an entire frozen continent with a single campfire. The amount of energy locked up in raising the temperature of an entire planet's surface and thickening its atmosphere is not just big numbers, big. It's the kind of big that starts to look like star-level projects. Just to warm Mars by tens of degrees on average, you're talking about energy on the order of what our entire civilization uses over centuries. And that's just the heating. Maintaining it against losses to space, because the atmosphere will keep leaking away over time, is an ongoing cost. And remember, Mars's air is mostly CO2. That's a good greenhouse gas, but it's not breathable. You can't just make it thicker and call it done. To have oxygen you can breathe without your lungs failing, you either need plants or machines, in mind-boggling numbers, to split CO2 and H2O and build up O2 over time. On Earth, it took photosynthetic life hundreds of millions of years to slowly poison the atmosphere with oxygen to levels that allowed complex animals to evolve. On Mars, even if we supercharge that with biotech, we're not talking years, we're talking lifetimes stacked on lifetimes. So let's register one constraint: terraforming, in the classical sense, is a project on centuries to millennia timescales. Not a presidential term. Not a venture capital cycle. Civilizational time. Now, we also have to deal with temperature. Mars is about 1.5 times farther from the Sun than Earth is. The sunlight is weaker, less energy per square meter. The average surface temperature is way below the freezing point of water. If you want liquid rivers, lakes, rain, you have to crank up the global thermostat by dozens of degrees Celsius. Again, we can imagine ways, greenhouse gases like carbon dioxide, methane, maybe engineered super greenhouse gases that trap heat incredibly efficiently, covering parts of Mars with dark material so it absorbs more sunlight. Even giant mirrors in space focusing extra sunlight onto the poles. All of that sounds like science fiction, because it mostly is, today. But in principle, none of it violates physics. It just stretches our engineering imagination. Then there's radiation. Without a global magnetic field, Mars is bathed in high-energy particles from the Sun and from cosmic rays. On the surface, the radiation dose is something like 2 to 3 times higher than on Earth, possibly tolerable in the short term with shielding and good medical care, but concerning if you're planning to raise children and grow old there. One concept people propose is placing a giant magnetic shield at what's called a Lagrange point, specifically, the point between Mars and the Sun where gravitational forces balance out. This artificial magnetosphere would act like an umbrella, deflecting solar wind away from Mars, helping protect the atmosphere from erosion and reducing radiation at the surface. Picture it, an enormous, invisible magnetic bubble, generated by a station in space, helping a whole planet hold onto its air. It's a beautiful idea. It's also an engineering project so vast that it makes our biggest machines, colliders, orbital stations, power grids, look like Lego sets. So if we lay it out, to truly terraform Mars, we need to thicken the atmosphere, warm the planet, shield it from radiation, and maintain all of this against ongoing losses. The timelines are centuries or longer. The energy budgets verge on star scale. The logistics make the Apollo program look like a weekend hike. And we haven't even touched one of the hardest problems yet, gravity. Even if we solve the air and the temperature and the radiation, Mars's gravity remains about 0.38 g, and gravity is not something we can easily change. You don't get to dial up a planet's mass without importing another planet. There's no known technology that lets you wrap a world in fake gravity short of massive rotating habitats. On the surface of Mars, your bones, your muscles, your heart, your brain, all of these are tuned by evolution for 1 g for Earth. The International Space Station has given us data on what happens when humans live in microgravity, 0 g for months. We see bone loss, muscle atrophy, changes in the cardiovascular system, vision problems, fluid shifts. Mars is not 0 g, but it's also not Earth. We really don't know what happens to a human body, or especially to a developing fetus or a growing child, after years in 0.38 g. Will bones mineralize properly? Will hearts grow strong enough? Will brains wire themselves differently? So here's our first paradox. Imagine we spend 500 years, trillions of dollars, and the creative energy of generations to make Mars a world with blue skies, liquid oceans, rich soil, and a breathable atmosphere. And then we discover, oh, Baseline humans still can't safely live here for a whole lifetime without serious health consequences because of gravity. Is that a terraformed planet, or a very expensive simulation of one? File that question, we'll return to it. Now, let's turn the lens around. What if, instead of changing Mars, we mainly change us, and our immediate habitats? We already have the beginnings of this toolbox. On the biological side, we have CRISPR and other gene editing tools. These are molecular scissors and pens that let us cut, paste, and tweak DNA, the long molecule that encodes how our cells build and repair a body. DNA in this story is like software that evolved over billions of years. It's not clean, elegant code. It's a sprawling, hacked-together, backward-compatible mess that happens to compile into you. But it is editable. Evolution has been editing it blindly for eons. Now we are learning to edit it deliberately. We also have nature's existing experiments. There are organisms on Earth called extremophiles, life forms that thrive in conditions that would kill most others. Some bacteria, like Deinococcus radiodurans, can survive radiation doses thousands of times higher than what would kill a human. They do this by having incredibly robust DNA repair machinery. Their cells get shredded by radiation, and then they stitch themselves back together. There are microbes that live in boiling hot springs, others in concentrated acid, others in rocks kilometers underground, feeding off the chemistry of stone instead of sunlight. So one path to self-terraforming is this. We look at Mars and we ask, what environments does it offer? Cold, thin air, lots of radiation, low gravity. And then we ask biology, what tricks do you already know that we can borrow? Could we, in principle, engineer humans with enhanced DNA repair, inspired by radiation-tolerant bacteria? Could we tweak skin pigmentation and melanin to offer more radiation shielding? Could we alter hemoglobin, the molecule in our red blood cells that carries oxygen, to work efficiently at lower oxygen pressures, like high-altitude Sherpa populations on Earth, but pushed further? People living in the Andes or the Himalayas have, over many generations, evolved adaptations to low-oxygen environments, larger chests, different hemoglobin behavior, more efficient oxygen use. They are, in a sense, partially self-terraformed for their niche. Could we do that in a few generations of bioengineering, instead of 1,000 generations of natural selection? We might also tweak how bones respond to low gravity, nudging them to maintain density even when mechanical load is reduced. Or give cells built-in scaffolding that resists atrophy, the way some animals resist osteoporosis. And then there's physiology beyond the genetic level. We can imagine devices and implants, cybernetics. Think of exoskeletons that mitigate some of the issues of low gravity by providing artificial resistance, making your muscles and bones work harder so they don't melt away. Or embedded sensors that constantly monitor radiation exposure and cellular damage, triggering targeted repair mechanisms. Life support systems could be woven into clothing, or even into the body itself, artificial organs that scrub CO2 from the blood more efficiently, or microreactors that generate heat locally in a frigid environment. On top of that, instead of trying to make the whole planet Earth-like, we can create pockets of Earth within it, habitats. Imagine underground cities carved into Martian bedrock, using the planet's own mass as radiation shielding. Picture vast caverns with pressurized air, artificial sunlight panels, forests under rock, rivers and tunnels. Or giant rotating habitats, O'Neill's cylinders, hundreds of meters or kilometers long, spinning to provide artificial gravity. Inside, you can dial the gravity up to Earth-like levels while the outside faces the harshness of space. In that model, Mars isn't so much terraformed as it is civilized with bubbles, little pockets of human-friendly physics embedded in a fundamentally alien world. Now let's do a very rough, back-of-the-envelope audit. On one side, full planetary terraforming. On the other, advanced habitats plus targeted self-modification. Energy is a good universal currency to compare with, even if we're wildly simplifying. To meaningfully heat and thicken an entire planet's atmosphere, you're engaging with an object that's 6 quadrillion tons of rock and dust and ice. The surface area is enormous. The atmosphere volume you're trying to build is vast. The energy budgets start nudging into, let's rewire star output, territory. In contrast, building and maintaining habitats for, say, 1 million people, or 100 million, is energetically expensive, but it's in a completely different league. It's like the difference between trying to warm the entire ocean versus warming a single swimming pool. A planetary ocean of air versus a few million cubic meters enclosed in engineered shells. City-scale engineering versus star-scale engineering. It's still a hard problem. You're running life support systems indefinitely. You're recycling air and water, producing food, handling waste, repairing radiation damage to structures, generating power. But every watt of energy you expend directly serves actual humans in a relatively small volume. You are not desperately trying to coax an entire cold world across a climate tipping point and then hold it there for millennia. From a pure physics and engineering perspective, self-terraforming plus habitats is dramatically more tractable than full planetary terraforming, at least on any time horizon shorter than. We've become a Kardashev Type 2 civilization, the kind that manages energy on the scale of a whole star. But there's another twist in this audit. We actually have a prototype for terraforming already. It's called Earth. Over the last couple of centuries, humanity has unintentionally become a planetary engineer. We've pumped greenhouse gases into the sky, changed the chemistry of the oceans, cut down forests, moved species around continents. The word for this is the Anthropocene, the age of humans, where our collective activity is shaping the planet's climate and ecosystems. In other words, we are already running a terraforming experiment. It's just that we didn't plan it very well. What have we learned from that uncontrolled experiment? We've learned that climate systems have complex feedbacks. You tug on one part, say, by burning fossil fuels and releasing CO2, and other parts respond. Ice melts, changing how much sunlight is reflected. Oceans warm and expand. Weather patterns shift. Some feedbacks amplify your initial nudge, others dampen it. The system is not a simple thermostat. It's more like a nest of interconnected springs and gears, where pushing one part can make a different part jump unexpectedly. We've learned that ecosystems are fragile in ways we didn't expect. Remove one keystone species, and an entire web of life starts to unravel. Introduce an invasive species, and centuries-old balances collapse. And we've learned something ethically heavy. Once you start changing a planet, you acquire a responsibility you cannot easily surrender. You don't get to say, "Oops, never mind," and walk away. The changes linger, sometimes for thousands of years. This is our only real case study for large-scale planetary modification. And it suggests that, "Let's just terraform Mars," is not a casual engineering proposal. It's a commitment that would bind not just us, but countless future generations, to managing a world whose responses we only partially understand. So if terraforming Mars is hard, slow, and ethically loaded, and self-terraforming plus habitats is comparatively easier and more targeted, why are we still even debating this? Because the physics is only half the story. The other half is who we are willing to become. Let's revisit that gravity paradox, the gravity trap. Suppose we somehow fix the air, the temperature, and even the radiation on Mars. The sky is blue. The air is breathable. The radiation levels are down to something comparable to high-altitude regions on Earth. It looks like a different world from the Mars we know. But gravity is still 0.38 g. We send colonists. They live there for decades. Children are born and grow up under this gentle pull. Their bones grow differently. Maybe they're more fragile by Earth standards, or maybe they adapt in compensating ways we haven't predicted. Their hearts pump against less resistance. Their inner ear and balance systems normalize to weaker gravity. Their entire sense of down is tuned to Mars. Now bring one of those Martian-born humans to Earth. Suddenly, Earth's gravity is crushing. Their bones and muscles are under nearly 3 times the load they evolved in. Their heart strains. Walking feels like wading through syrup. They may not be capable of long-term survival in 1G without extensive medical and technological support. In that situation, we have to ask, did we actually terraform Mars for humans? Or did we create a new branch of humanity primarily adapted to Mars, Martians who cannot easily return home? And here's an even sharper edge. What about pregnancy and childhood development in low gravity? We genuinely don't know what happens when a fetus develops in 0.38 g. Does the heart form correctly? Do bones form properly? Are there subtle neurological changes? Does the vestibular system, the inner ear balance organs that also tie into brain development, wire differently? If the answer is, we don't know, and the risks are high, then if fully terraformed, Mars might still be a world where baseline humans are not safe to reproduce. We might fix the environment as we measure it, temperature, pressure, radiation, but miss the hidden variable of gravitational context. So even in the classic terraforming dream, we may end up needing self-terraforming, genetic tweaks, mechanical assistance, artificial gravity habitats for gestation and early childhood. Suddenly the dichotomy, change the planet versus change us, starts to blur. Now let's look at radiation through the same dual lens. There are 2 broad strategies: shield the planet, or shield the cell. Shielding the planet looks like big infrastructure, thickening the atmosphere, creating artificial magnetic fields, building underground cities, or covering settlements with meters of regolith, Martian soil, to absorb cosmic rays. We try to recreate, at large scale, the protective layers Earth has: magnetosphere, thick air, strong rock. Shielding the cell means going inside the problem. Instead of deflecting radiation before it hits us, we change how our cells respond when it does. We could, in principle, engineer more robust DNA repair systems into human cells, inspired by extremophiles. We might increase natural antioxidants, tweak proteins that sense DNA damage and coordinate repair, or even add entirely new biochemical pathways that recognize and fix radiation-induced damage. We might increase melanin production or invent new pigment molecules that absorb or scatter harmful radiation before it reaches sensitive cellular machinery. We might design nanomachines, molecular-scale devices, that patrol our cells, scanning for breaks in DNA or damaged proteins, repairing them on the fly like microscopic mechanics. From an information theoretic standpoint, we're comparing two very different challenges. One is trying to rewrite the environment's physics as experienced by a planet. That's like trying to edit the weather. It's possible to influence, but it's messy, emergent, nonlinear. The other is editing code, our biological code. As messy as biology is, the genome is, at least in principle, a sequence of instructions. Is it harder to build a global magnetic shield that bends streams of charged particles tens of thousands of kilometers wide, or to teach a cell to recognize and repair one more type of DNA damage? There's no simple answer, but the latter is, in many ways, a more targeted manipulation. You change a few bits in the code, and the organism's behavior changes everywhere in its tissue. But now the stakes jump from physics into identity. Because if we go down the path of heavy self-terraforming, genetic redesign, cybernetic augmentation, radical physiology, we have to face something I'll call the identity drift problem. Imagine a child born on Mars in the year 2600. Their parents were part of a colonist wave that embraced self-modification. The community had decided that, to thrive on Mars, you don't just wear the environment, you become the environment. So this child is shorter than average by Earth standards, less need for tall frames and low gravity. Their bones are laced with engineered proteins that keep density high despite the weaker tug. Their skin is darker, not because of heritage but because of engineered melanin tuned to Martian sunlight and radiation frequencies. Inside, their cells carry extra copies of DNA repair genes borrowed from extremophile microbes. Their blood chemistry is altered so they can function fine in lower oxygen atmospheres. They also have a neural interface, a safe, well-tested cybernetic implant that links their nervous system directly to local networks, to augmented reality overlays, to swarm robots that help maintain the habitat. They are healthy. They are thriving. Their brain is not less human, it's just plugged into a wider sensorium. They call themselves human. Their community calls itself human. Now fast forward another 300 years. The modifications accumulate. Some groups on Mars decide to push further. They adopt partial synthetic organs that can handle perchlorate contaminated water or extreme temperatures. They shift their circadian rhythms to match Martian days more precisely, 24.6 hours instead of 24. Their average body plan diverges, maybe more flexible spines for lower gravity, different skull shapes to accommodate neural implants. At what point do we say, these are no longer just humans who've been tweaked? These are a new branch, a sister species. This is the ship of Theseus problem, applied to biology. The classic thought experiment goes like this: you have a ship. Over time, you replace one plank, then another, until every single part has been swapped out. Is it still the same ship? With self-terraforming, we're doing that to ourselves. One upgrade here, one genetic edit there, one neural implant, one artificial organ. When, if ever, do we cross a threshold where the entity looking back in the mirror is, in some deep sense, not us anymore? And who gets to decide where that line is? Because woven through all of this is power. If we go the planetary terraforming route, the levers of control tend to be centralized. You have massive organizations, governments, planetary councils, megacorporations, running the climate machines, the atmosphere factories, the orbital mirrors. Decisions about Mars's future environment become geopolitical. They involve treaties, wars, sabotage, monopolies. If someone controls the machines that keep the air breathable across a whole world, they control everyone who needs to breathe. If we go the self-terraforming route, the levers of control shift. Now the crucial question is, who controls the template of a Mars-adapted human? Who designs the gene edits? Who approves the implants? Who owns the patents on enhanced lungs or radiation-resistant cells? We risk creating new castes. Imagine baseline, Earth humans, people who never left, or who choose to remain genetically unmodified, looking up at off-world populations who are taller, smarter, more radiation-resistant, adapted to different day lengths, able to plug their brains into quantum communication networks. We could end up with a split civilization, Earthbound baseline, and optimized off-worlders. The power dynamics there are not hard to imagine. who gets access to what resources, whose voice gets priority, whose definition of normal becomes legally enshrined. In one path, the environment becomes political property. In the other, the body and mind themselves become political property. And then, peeking just beyond that, there's another escape hatch. We might sidestep both paths without intending to. Call it the simulation escape hatch. Suppose we build advanced habitats on Mars, domed cities, underground forests, rotating space structures in orbit. Inside these, we can control the environment very precisely: temperature, air mix, lighting, sound, even gravity if they're rotating. Now add advanced virtual and augmented reality. Inside your Martian city, you put on lightweight AR lenses or neural interfaces. The walls disappear. You see beaches. You walk through forests that are half physical, half projection. You meet friends whose avatars look like anything they want. The simulated Earth, or simulated exotic fantasy worlds, feels, for most purposes, more real to your brain than the actual red desert outside. From the outside, it looks like we've colonized Mars. Humans live there are cities, there's industry. But from the inside, most people's subjective daily experience might be in layers of simulation. Have we colonized Mars? Or did we just move the server rack? If your whole life on Mars is spent in curated realities, using the physical planet mainly as an energy source and a place to anchor hardware, the line between living on Mars and living in cyberspace that just happens to be physically stored on Mars becomes thin. So, change the planet, change ourselves, or change the reality we experience. Each path raises its own philosophical audit. Let's pull back now and ask, what does any of this say about being human? Because beneath all the physics and biology, there's a quieter decision being made. If we insist on making Mars like Earth, as much as possible, we are implicitly saying, our current form is non-negotiable. We're fragile animals that require a very specific atmospheric pressure, a narrow temperature range, exactly 1 g of gravity, a very particular mix of gases. In that story, being human means being this kind of ape, in this kind of environment. Any world we settle must bend itself toward that template. We are the static thing, the planet is the variable. If we instead lean into redesigning ourselves, we're saying something radically different. We're saying, human is a moving target. It's not a fixed state, but a pattern, a functional, psychological, cultural identity that can inhabit many substrates and environments. Biological flesh adapted for Earth, modified flesh adapted for Mars, digital minds in silicon running in the cold shadows of the outer solar system, these could all, in principle, claim continuity with something we call human. In that vision, the universe stops being a hostile backdrop and becomes an invitation to adapt. And that fits, in some sense, with the deep story of life. For billions of years, life has been an engine of adaptation. Organisms change to fit worlds, deserts, oceans, ice shelves, volcanic vents. Evolution's motto, if it had one, would be, whatever works survives. Life does not complain that Antarctica is too cold or that the deep sea is too dark. It either finds a way to fit, or it dies. Now, for the first time, intelligence, technological, reflective intelligence, gets to invert the relationship. We can imagine worlds adapting to life, not just life adapting to worlds. Terraforming Mars is us saying, we will take this dead rock and paint it with conditions suitable for our branch of life. We will extend the niche of Earth biology. But at the same time, with genetic engineering and cybernetics, life can now adapt itself intentionally to worlds that don't care about its comfort. So which do we choose? Or do we choose both? Before we answer, there's one more audit we need to make. The homeworld audit. Right now, as you listen to this, we are mid-project in an uncontrolled terraforming of Earth. We are changing the composition of the atmosphere. We are acidifying the oceans. We are altering the reflectivity of the planet's surface by cutting forests and changing land use. We are building cities that create heat islands, rerouting rivers, melting ice that has been stable for tens of thousands of years. If an alien civilization were watching us from afar, they might say, this species is transitioning. They are beginning to engineer their climate. Let's see if they do it on purpose or by accident. So one ethical question is, should our first terraforming project be to re-terraform Earth, to bring our homeworld back into a sustainable, stable configuration, before we export that process to other planets? Because there is a risk that we go to Mars, or beyond, carrying the same mindset that led us into trouble here, treating atmospheres as externalities, ecosystems as expendable, long-term feedbacks as someone else's problem. If we can't manage the feedbacks of one habitable planet we evolved on, are we ready to manage the feedbacks of a hostile planet we barely understand? And yet, there's a contrary argument. That by trying to terraform, or self-terraform, elsewhere, we might learn lessons that help us heal Earth. That building closed ecological systems on Mars could teach us how to run more efficient, circular economies on Earth. That pushing our understanding of climate manipulation could yield tools to carefully, cautiously, nudge our own climate back towards stability. In reality, our future is unlikely to be a clean either-or. The most plausible path is a messy, creative synthesis. We will probably do partial planetary engineering on Mars, localized warming, dust management, maybe attempts to release more atmosphere from ice and rock, perhaps even small-scale magnetic shielding. We will almost certainly rely heavily on advanced habitats, domed cities, underground networks, rotating stations in orbit, each a little pocket of curated physics. We will also, if history is any guide, modify ourselves. Some changes will be subtle, vaccines that tweak immune systems, genetic edits that remove disease risks, sensory augmentations that improve night vision or radiation detection. Others might be more radical in frontier communities willing to push boundaries. In that hybrid future, every settlement, every generation, will be negotiating the boundary between organism and environment. How much do we ask the world to bend to us? How much do we bend to it? Where do we draw the line between acceptable adaptation and I no longer recognize us? Let's go back one last time to that image of stepping onto Mars. You stand, whoever you is, centuries from now, on the edge of Valles Marineris, that canyon system so vast it makes the Grand Canyon look like a scratch on an orange. The sky above you might be bluer than it is today, or still thin and red. The sun is still small. Phobos and Deimos, Mars's tiny moons, still crawl overhead. You take a breath. Do you need a helmet? Or are your lungs, your blood, your skin fundamentally different enough that this thin, engineered air is enough? Do you walk with an easy spring in low gravity because your body is built for it, or are you wearing exoskeletal support that quietly adjusts the load on your bones? If this future Martian looks back at us, at 21st century humans, who are we to them? Ancient prototypes? Cautious ancestors who refused to alter their DNA? Barbaric tinkerers who accidentally terraformed their own planet and nearly broke it? Or the first species to realize that human was not an endpoint, but a question? Because that, ultimately, is where this audit lands. When we talk about terraforming Mars, or self-terraforming to live there, we are not just planning engineering projects. We are casting votes on what kinds of beings get to call themselves human. Do we anchor that word tightly to a particular set of biological parameters, a specific range of heights and bones and lungs and unedited genomes? Or do we allow it to stretch to include Martian-born children with reinforced skeletons and built-in cosmic ray repair? Do we extend it further still, to digital minds running in Martian data centers, embodying our memories and values without a drop of blood? There isn't a right answer baked into physics. The universe is silent on definitions. It just offers constraints and opportunities. So here's our synthesis. Terraforming a planet like Mars, in the classical science fiction sense, a blue sky, thick atmosphere, Earth-like climate, is an undertaking on civilizational timescales and star-scale energy budgets. It's possible in principle, but unimaginably hard in practice. Self-terraforming, modifying humans and building advanced habitats, is, comparatively, a city-scale problem. Still enormous, but within plausible reach of a future industrial civilization. Yet the easier path technologically is the harder path philosophically. Changing Mars keeps our bodies sacred and the world malleable. Changing ourselves treats our bodies, and perhaps even our minds, as clay. Radiation, gravity, climate, at every turn, the audit reveals that the neat boundary we like to draw between environment and organism is illusory. We are already coextensive with our world. On Earth, we've learned that nudging the climate nudges us. On Mars, we will learn that nudging us nudges what we mean by home. The likely future is not Mars or us, but Mars and us changing together. So here's a contemplative takeaway, a thought experiment to carry into your own life. Pick one aspect of yourself that you consider non-negotiable. It might be physical, your face, your height, your voice. It might be psychological, your sense of humor, your memories, your moral instincts. Now imagine a scenario where changing that one thing would let you, or your descendants, step out onto Mars without a suit. To feel that cold red wind on bare skin and not die. To build a civilization under a salmon sky. To write poetry about 2 moons instead of 1. Would you change it? At what point, as you imagine stacking changes, one after another, do you start to feel that a line has been crossed? Is it when your bones are reinforced? When your skin pigments shift? When your circadian rhythm adjusts? When a neural implant starts sharing some of your thoughts with others? The discomfort you feel, that sense of, no, not that. is the edge of your personal definition of human. It's the same edge we, as a species, will be negotiating as we decide how far we're willing to self-terraform for new worlds. And finally, the next great question, because every answer just opens a new door. If we eventually discover that, from physics' point of view, it really is easier to change us than to change Mars, and we take that path, editing bodies, augmenting minds, what happens to the continuity of who we are? If time is an illusion assembled by our brains, a useful story stitched from memories, then as our brains and bodies change, what does that say about the memories we hold most dear? When a Martian-born child with an engineered genome remembers stories of blue Earth oceans they've never seen, passed down from us through recordings and neural imprints, are those still our memories? Or have they become something new entirely? That's where we'll go next time on the Science Audit. For now, as you look up at the night sky, maybe pick out that faint red dot if you can. Ask yourself, not just, could we live there? But, who would we be if we did? And how much of what you call you is gravity, air, and sunlight, that you've never even thought to question?